So just once again, if you forget your trends, just go to your data booklet and you can look them up. But the mark scheme will be about explaining usually. So first of all, just experimentally, you can get light emitted from hydrogen gas and put it through a prism. And then you'd use a spectrometer, which is basically a prism, and in a dark sort of like box, so you can actually see the light that comes off. Now that's this range here. More expensive equipment will allow you to see ultraviolet. We'll be able to detect it. But if you keep on exciting the electron, it's not going to keep going back and releasing electromagnetic radiation. There's going to be a point where it just goes off into space, as you like. And so that's what ionization energy is. And so you can actually see here that there is convergence, that the shells are getting closer together. So we can directly measure these things and even see them with our eyes in a high school experiment. So first of all, the equation, which is often asked for, is a good way to is better than a definition in my view. You can see there is 1 mole of electrons that has been removed. There's the 1 mole of electrons. There's the first mole that's been removed, so it's only plus, and you can see they're both in the gaseous stage. So that is quite nice to be able to do that quite simply. So first of all, the group trend, I've just chosen group 1 here. I could have circled maybe the halogens at the top, but you can see that as you go down a group, the first ionized energy decreases. This is because the electrons are in outside shells, and so they're further away from the nucleus. Therefore, there's less attraction. So the nucleus is actually increasing, but the effective nuclear charge is decreasing. So the attraction of the electrons to the nucleus decreases because it's further away. Therefore, it's easier to take an electron away. So going across, now in some graphs, you won't see these little anomalies here, just here and here. You'll only be able to see it just go straight up. And so that is because they are all in the same energy level, the same distance. The electrons are the same distance from the nucleus, but the nuclear charge is increasing. Therefore, the electrons have a stronger attraction to the nucleus, and it takes more energy to remove that electron from the nucleus. So ionization energy increases across a period. Two other things that are often asked to be explained in these graphs are the big jumps. And so you can see from a full shell, a noble gas, the ionization energy is quite high because it's a stable electron configuration. That's what everyone's trying to get. Whereas if you just add 1 electron, these guys all just are the next shell up with just 1 electron, and so they want to do the exact opposite. They actually want to lose an electron to become helium or neon or argon, and so they are unstable and actually want to become stable, and so they actually want to lose their electrons, and so there's these huge gaps. So it wants to have a full electron shell, so it quite happily loses it and goes down to the next lower energy level. Okay, so these are describing where the main energy levels are. So that's energy level 1, or everything along here, and everything along here is energy level 2. And so there's the big jump. The other 2 small anomalies that I was talking about before is very similar because you can see in the first instance it has not a full valence shell. It's not completely full, but the subshell is full, which is an element of stability. So it likes that and would rather have that than have just 1 electron filling in an incomplete subshell. And so it takes more energy to remove an electron from here because it's already a full subshell than removing an electron from a half-filled subshell. Okay. The next one is also quite useful for your SPDF electron configurations. To realize that a completely half-filled subshell is also stable. And so it would rather have that than this situation here. Now that is an extra electron that's in close vicinity in the subshell, and so that actually something called a new term here called mutual repulsion. And so that is unstable, and it's easier to remove the electron from there instead of the electron from Not as stable as a full subshell, but a halved full subshell has some stability also. So that explains the last one.